Hello everyone and welcome to Handmade, here the show where we code a complete game live on stream. Except for not coding complete game live on stream today, we have an interim thing to do, which is load PNGs. So we're actually going to be writing an IDAT decompressor live on stream. Gotta have coffee for that, my friends. So what we did yesterday is we broke into the PNG spec. We pretty much figured out what was going on at the high level, which is pretty straightforward. It's a very simple RIF style format, basically. And what we did is we wrote something that parsed that and found out the data that we needed, and then has the data stream sitting there that's the actual compressed image data, but we didn't have a chance to actually get down and dirty with that and figure out how to decompress that. Now, we did read about how to decompress that, so we're kind of ready to go, but we didn't have a chance to actually code it. Now again, we are not trying to write a complete or even a fast or efficient PNG reader. We just need something that reads PNGs at all. And the reason for that is we want to enable a quick turnaround time in Photoshop. And that's all we're doing right now. So what I want to do here, let me go ahead and load this up. Here's our parse PNG. So what I want to do here is pick up where we left off yesterday, which is to say that once we see these IDAT chunks, we now need to do something with them. Now, I'm fairly certain, even though the spec was kind of cagey about this, I don't feel like they said it in a very good or clear way. That's okay, because we kind of figured out, we more or less figured out what was going on. What I think is happening here is when you encounter these IDAT chunks, they're just chunked data that's actually all one stream, right? And the reason that I say that is because the spec for an IDAT chunk clearly states that it will have the ZLIB information at the front. And what we can see is this, even though it's a very simple PNG, what we can see here is that we have 4 IDAT chunks, and the 4 IDAT chunks are not IDAT compliant. Only the first one is, which has the ZLIB information. So what that tells me in terms of how I'm going to approach this first is I'm going to assume, even though the spec I don't feel like was worded very well, so it wasn't clear on this, I'm going to assume what they meant when they were talking about IDAT chunks was that actually the IDAT chunks are all one stream that you parse as if it was contiguous, even though it kind of suggested that IDAT chunks start with this particular header. I think what they mean is the first IDAT chunk does, and then it did clearly say in the spec that IDAT chunks all have to come together and that they are interpreted as one group. And so I feel like that was them trying to say there's only going to be the ZLIB header on the first one, right? So I think what that means, unless I'm very much mistaken, is that we read the ZLIB header out of the IDAT chunk that comes first, and then we just read the rest of the stream, including all future IDAT chunks and all of the data inside those IDAT chunks, as being just part of a ZLIB deflate stream, and we assume that they don't ever have any other ZLIB startup information in them. Now that could be wrong, but that's what I think they're trying to say. And what that means is that the PNG, in this case, can only have one compression mode, or not one compression mode, one ZLIB header for the entire compressed data section. That's what it looks like. I could be very wrong about that. We'll find out as we go forward. But that's what I was able to determine so far, and so that's the assumption that I'm operating under, and you'll see me operating under that assumption for the remainder of the stream until we encounter something that gives me a clue that I'm wrong. Okay, so now, jumping back to where we were, when we were decoding this, when we grabbed out all of this information, what we ended up finding was that we have these sort of ZLIB informational pieces here, and what we are told, anyway, in the spec is that the ZLIB information should never actually allow us to see a CM value, which I believe stands for compression method, or at the very least it means compression method. We should never see a CM value of anything other than 8. So in other words, it has to be a CM8 here. There's nothing else that it can actually be, I believe. Now I could be wrong about that, but if we go back here to the compression information, we'll just reread it again to make sure I'm not wrong. But here's the compression section, and what it says is Only PNG compression method 0 is defined by the international standard. Other values of compression method are reserved for future standardization. That 0 is the thing that was in the header, so up here, right? And you can see when we actually dumped it, we got exactly that, right? So then when we come back here and we look at the ZLIB information, going forwards, it says, okay, so PNG compression method 0 is deflate inflate compression with sliding window from the LZ77 deflate standard that comes from the ZLIB library, right? So then it says that it has to come with this header. Compression method flags and code is 1 byte, additional flag checkbooks 1 byte, the compressed data, and then the check value, right? That's what we're expecting to see. Now, it's kind of odd that we have a check value at the end, given the fact that these blocks have a CRC themselves due to the PNG. Don't ask me why, that's just what we've got. So off we go, right? Now, what I don't actually know is whether or not there's additional ZLIB startups inside the stream. So even though the IDAT chunks might not have ZLIB restarts, maybe there's ZLIB restarts elsewhere in there. I'm not sure. We'll look at that as we kind of go forwards. Anyway, for PNG compression method 0, the ZLIB compression method flags code specify method 8 and not more than 32K of window, right? So that's where I'm getting the like this has to be 8 thing. So I believe we only have to support CM method 8. So what I want to do here is sort of say, all right, let's take a look at this in a slightly different way. What I want to do here is I want to make something that's going to allow me to read from these IDAT chunks as if they're continuous, because I'm expecting to see this thing want to read a continuous stream across IDAT chunks. So what I want to do is when I see the first IDAT chunk, I kind of want to, I don't want to start processing here because I don't know where the rest of the IDAT chunks necessarily are. Now, it's said in the spec that the IDAT chunks have to be contiguous. I could take their word for it, or I could just build a chain of them a priori, which might be what I want to do. All right. So if I wanted to do that, how would I do it? Well, let's take a look here. So I think I've got, if I look up here, I've got this notion of entire file, where we've got the content size and the contents here, right? That sort of stuff. I think what I might want to do is kind of broaden that a little bit, maybe. I'm just thinking out loud here. But suppose we were to do something like this, where we said like, okay, we've got, you know, I don't know, a streaming buffer, and it has something like this. And when we stream stuff, maybe we've got a thing that's like this. So we can kind of like chain these things together, where we can just make like a list of them and say like, ah, yeah, we're going to read all of these things in, right? And I might want it a little bit different than this, right? I might want to do something like this. So I can just sort of have an idea of the stream that I'm reading in here, and I can just kind of like navigate through them in some kind of reasonable way, right? And so what this would do is it would say like, oh, okay, you know, when we read in an entire file, we want to be able to just do one of these, and we can, right? So when we have a situation where we're doing a streaming chunk, a streaming buffer like that, we can read in an entire one and just get like sort of this stuff initialized to 0. So off we go on this. It'll just return exactly the same thing that it was returning, and this will operate on this, right? Why do I keep doing that? And then what we would do is when we get an underflow, what we want to do instead here is say, look, if we get an underflow, let's actually try to look at the next chunk in the thing. So what we can do is say, oh, well, if content size exactly equals 0, we can assume that the person who was reading out of this thing was reading out of it in a sensible way, and wants to just get maybe what's in the next chunk, right? So what I could do here, let's see, maybe I'll do it like this. I don't really know if I want to do it like that exactly, but maybe like that. So what I want to do here is say, all right, look, if the content size is enough to fulfill the request, then do it. If the content size is 0, then maybe we want to advance and get the thing out of the next chunk. We could be even more creative here and actually try to assemble things together into pieces. I'm not actually going to do that, but I could show how to do that. There's other ways we could do that. There's ways to construct buffers for streaming that do that. But what I want to do here is say, look, if we just assume for now that everyone's reading the right amount of stuff in, then in that case, what I'm going to do is advance to the next one. So what I'm going to do is say, in fact, I can do this like this. So in that case, what we'll do is say first, we'll grab out streaming chunk this. We'll set file first equal to this next. And that'll knock out to 0 eventually, right? And then what we'll do is say, okay, when we grab the first one out of here, we'll set the content size that we're looking at now. And the contents pointer itself to be the one in the next chunk, right? So this is just kind of a quick and dirty, not particularly well thought out or anything, just a random crappy way of making a buffer that can have multiple chunks in it, right? And so if I compile this now, I should be able to do a thing where we can just recompile what we've got here. And this should still work, hopefully. Let's see. Oop. Got a bug somewhere. There we go. Yeah. In fact, I suppose what I could do is just do this again. It's short enough that that loop seems kind of dumb. Right? What I could do is just say, all right, look, just repeat this. Like so. Like that. And I could just put that at the top, in fact. Now this is looking much nicer. So if the content size is 0 and there's a file first, in fact, this is what we'll do. We'll just say, oh, all right. Well, in that case, we advance it. And then we try to do the thing we were going to do. That's much better, right? Yeah, much nicer. So we just say, all right, look, if the content size is 0 and there's another one, let's advance to the next chunk first. So that's this, right? And then we'll keep going, right? Let's do what we were going to do before. That's much saner. So now what we can do is we can build up one of these guys. We can build up one of these sort of chains for all the IDAT chunks. And then when we're done, we can decompress the image, right? So what I want to do here is say, all right, let's move this stuff out to something at the end. Well, I guess you know what? I don't need to put it there. It can just be here. So allocate pixels can come here, which is great. There we go. So here we go. We say if we got the file header, while we read it, assuming that we end up with one that's supported, we will go ahead and try to decompress it later. And what we'll do is we'll just build up the IDAT chunks that we actually want to use here. And the way that we'll do that is we'll just say, let's pretend that we have an IDAT sort of, or pixel data, I don't know, compressed data or something. Let's assume that we have a streaming buffer of compressed data, and all I'm going to do is every time we get in here and find one of them, I'm going to add it to this, right? So what I'm going to do is say, okay, here on comp data, I'm going to need a streaming chunk. So I'm going to go ahead and do an allocate chunk here, like so. And the reason I'm putting these out here is because, again, I want to do stuff special with them when we integrate this code into Handmade Hero. So what I'm going to do here is say, all right, when I allocate a streaming chunk, I'm going to do it like this. That'll give me back one of those. And so as we encounter each of these, I'll just say allocate a chunk, and then I'm going to set the chunk up to be the data that's in this particular IDAT. So as far as I know, we use the whole IDAT chunk for the data, right? So we basically say, okay, this IDAT chunk has the chunk data here and the chunk size here. So I'm just going to use that. And then I just need to set the next pointer up. It's going to point to nothing because I want to append at the end. So then when I go to set the streaming buffer itself, which is the compression data, I just need to set the first and the last, right? Now, in any case, the last will always be equal to chunk because I'm appending to the end, right? So we kind of know that that's always the case. But the first will only be set in the case where, if comp data first is not equal to something, or, if last is valid already, so I already have one in there, then the comp data first doesn't need to be set, right? It's just comp data last next equals chunk, and then comp data last equals chunk. And at the same token, if it wasn't the case, if the first were, if the first wasn't set, then I would set it like this, right? So this is just a kind of a bigger way of saying I'm going to append to the end of the list. The next pointer will always be 0 because I'm adding it to the end of the list. But in terms of setting up the first and last pointers, well, the last pointer always needs to point to this chunk because it is the last one now. But the first pointer only gets set the first time I do it. And the last pointer gets its next pointer set if it was set to anything, right, in the other case. So these are the two cases I might have. This leads to my favorite ridiculous way of compressing this code, which people hate, but I don't really care, which is to say, hey, if comp data last is set, then I'm setting this, right? But if comp data last isn't set, then I'm setting this. Right? I'm setting these two, and I'm setting them equal to chunk. Oops. Makes sense? Right? That's what we were saying. So I'm saying, like, look, if the last thing is set, doesn't need a parentheses around it. If the last thing is already set, then I'm going to set the next pointer equal to chunk. If the last wasn't set, then I'm going to set first equal to chunk. But in either case, I'm going to set comp data last equal to chunk. So hey, since this whole expression evaluates to chunk, why not? And so that's the ridiculous way of doing a singly list append at end in one expression, for those of you who like obtuse code. Right? Again, just to be clear on that. So it's, right, comp data last is always going to be set to chunk, either way. And then the question is just which of these two do we also want to set to chunk? If comp data last was set, we set the next pointer, because it means that first is already set as well, because last and first will point to the same thing. Well, first will point to something and last will point to something, either it or after it. And then comp data first, in this case, is just the thing that is going to be set in the case where we haven't set anything yet. And then in that case, last and first will be set to the same thing. So anyway, that's all we need to do there, right? So all of that information just kind of gets buffered up. And then what we can do is from then on, we can just start to look at the stream as it comes in. So what I can do here is change this to a consume and say, well, the thing that I want to consume is the comp data. I want to consume a ping IDAT header from it and read that out and just print out what happens there, right? So let's see if we can make that work. We need to store the width and the height here, actually, though. Those are the only two things we allow to vary. And so I'm going to go ahead and put those here. There we go. Yeah. And what is the... There we go. Okay. So now, if we did that correctly, we should see ourselves read the IDAT chunks, and then we should come in here and decompress them, which is exactly what we did. Now, I'm going to print out, when I see this IDAT chunk, I actually want to see a little bit of information here as well. I think I'd like to see the size, just so I can know like how long each of these is, because I'm curious. So when I do this, let's see. So that's so again, this gives us a little bit of insight, I guess, into what's happening again, which is to say that, and let me just go ahead and okay, there we go. Which is to say that I was wondering what the idea is behind these IDATs, and you can kind of see from this pattern maybe something is kind of being suggested there, which is that it looks like for whatever reason GIMP writes these out in chunks of 8192, right? Which is 2 4K pages. Why it does that, I have no idea, but that looks like what they're effectively using these IDAT chunks for is buffered I/O. So I don't know if maybe GIMP has a buffer of 4K, 2 4K pages, so 8192 or 8K, that it just fills up and then flushes, fills up and flushes, fills up and flushes, and every time it flushes to a new IDAT chunk. Now, why it doesn't just flush to the same IDAT chunk, I have no idea, but it kind of looks like that's what it's doing. Maybe there's something somewhere that would explain this. I don't know what it is, but that's looks like what's happening. So then once we go to decompress, you can see that we get the same information that we were getting before, right? When we were reading the IDAT chunk directly, 872603, 872603. So now we're reading out of that stream nicely. And now we can begin to do the rest of the compression, right? And so this is the, decompression. So this is a part where you need to start figuring out what the heck they're doing here. And so we know that there's a window size that we need to be aware of. I don't know that we actually care about the window size very much, other than it may inform how the bits are encoded as to how many bits of window backlook we use. That's the only thing I could think of where that's actually even going to come into play, because we actually support the entire look-back window, because we're decompressing this into an image, and we will allow it to look back arbitrarily far. It can look back to any part in the image and grab any part of it because we have it all in memory. It's not a streaming decompressor in our case. So what that means is that we don't really care what the window size is, but it may tell us something about how many bits are encoded in the stream for a certain piece of information. So I don't know if we might need that later, but that's the only reason we would even need that. Anyway, so looking at all of this stuff, I think all we really care about here is to go ahead and use that data at the head end to start implementing this spec, right? So looking through here, when we see F level, I don't know that we care about this. Yeah, it says right here that the F level is not needed for compression. So really all that's telling us is how hard it tried to compress this data on the compression side, but we don't care, right? Similarly, fdict, I think we read that fdict was not allowed to be set. So I think this always has to be 0. I could be wrong about that, but I think that's what it said. So I think in here, we can actually do something like this. So this is the ZLIB headers here. So I think what we want to say is that supported is going to get modified here. So CM has to equal 8. Fdict has to equal 0, I think, right? Because I don't think we're allowing anything else in here. So then moving forwards, when we start decompressing, then we can allocate the decompressed pixels. And I think then now we're good to go. So looking back at the spec here, I think there's nothing more we can really glean from this, if I remember correctly, because this just says go read the other document for learning how deflate works, right? Yeah, I think so. Yep. So I think we're just living here now. This is our jam, and so this is what we want to actually do. We want to follow this rule. So like read block header, if stored with no compression, whatever. Like we want to do this. So what we need to do is we need to start reading said block header, right? And we need to figure out how we do that, right? What does the block header look like? And how do we determine whether or not we compress or don't compress? So it says each block of compressed data bits with 3 header bits, B final and B type, and off we go. So that's the first thing that we want to be able to do is kind of read these bits. Now, I'm loath to make something that literally reads bits, but at the same time, that's what we're going to basically be dealing with. So I think I want to do something that's like the worst possible thing here for a while. Because again, I don't really care about this code. I just need it to work. And if the stupid thing ends up working fast enough, then I'm not going to touch it, right? I'm just going to let it do its thing. So I think we want to do something that's literally the dumbest possible thing, where we can just basically say like get bit, like literally, right? So I kind of want to do something here that says B final, B type, right? I want to do something that basically just says, look, I think I want to do something like that, right? Where I can actually consume bits at a time and write the code that way and then just deal with the fact that that's not very efficient because, again, if it doesn't end up being a problem, I'm not going to care because this is not code that runs during the game. If it's stored with no compression, skip any remaining bits in current partially processed byte, read len and nlen, see next section, copy len bytes of data to output. So this is the uncompressed case. Which should be pretty reasonable, right? So what I want to do here is I need a flush byte call, I guess. So when we're doing consume bits, then we have a flush byte call, and the flush byte call is basically saying, look, as I'm taking bits out, I'm going to jump to the next 8. That's just what it says that it wants to do for whatever reason. Read len and nlen. I don't know how long those are, but presumably they're going to tell us in a second. And this happens if B type equals something. So 0, 0 is no compression. Then we've got compressed, compressed, and reserved, right? So we basically have a B type of 0 is going to do something. A B type of 1 is going to do something. A B type of 2 is going to do something. And any other B type, because we don't allow 11 in this case, is an error, right? And so that's going to be B type 3 is just not, it like the spec doesn't say. So we hope to never encounter this. And in theory, we shouldn't, right? So we have B type 0, B type equals 1, B type equals 2. I don't actually know if the fixed Huffman code version is supposed to happen, because I kind of think we've read something that says it's not. So I'm going to assume that the dynamic Huffman code is the only path for now. But I'm not sure about that, because it was kind of, the spec, again, was really not worded well, I didn't think. So I'm going to just see if we see any of these. If we don't see any, I'll assume that's the right reading. If we do see some, then obviously that was just erroneous. So then we've got the two cases here. Really, the dynamic Huffman code one is the same. These two are basically the same. So I guess what I could do is this. So if compressed with dynamic Huffman codes, so if the B type is 2, this reads the dynamic Huffman codes, and otherwise it doesn't, right? And so sort of what we're saying here is, I guess we're saying that. I'm sorry, no. We're saying this. Because I guess the idea here is that we're not expecting to be using the fixed Huffman codes. But if we do encounter fixed Huffman codes, it's okay. We would just set up the fixed Huffman table here, right? So this is like, right? And so then we start to do the loop block here, and this loop, I guess we look at B final. So in here, this is really a while loop. And, you know, I could literally code it that way. So basically, we're going to read in whether or not we should stop. But even if we should stop, we're still going to process the block because the last block is a valid block. The B final flag, if it got set, we will then end out of the loop and go from there. If we're inside, we're going to take a look at the B type. We've got a pretty easy one here that just does a consume. And we have to look up what these mean. We don't know quite yet what these values are, how many bits they are, or anything like that. But then we've got these sort of two other things. We've got the B type equals 3. That one is not specified in the spec, so we don't know what it is, and we're just going to bail if we see it. Otherwise, we've got the B type of 1 is the one we're expecting. I'm sorry, 2 is the one we're expecting. 1 we think might not be allowed in PNGs, but we don't know. And then we actually have to implement this loop, right? So we need a literal length value from the input stream, and we don't know how to get that right now, right? So we're going to get that. This is probably a Huffman decode here, right? Then we look to see what the value that we get out is. If it's less than 256, we copy a literal byte to the output stream. So basically what that's saying is if we read a Huffman code and that Huffman code has a value less than 256, it's actually putting new data that we've never seen before into the output stream. But if it's greater than 256 or greater than or equal to 256, then we're going to assume that it's actually an LZ jump back information. Now because people may not have done LZ before, let me just explain how these work. They're very simple, but they form the cornerstone of like all modern compression anyway, even though they're very, very basic. Oops. So things that conform to LZ style compression are really very simple in theory. The way that they work is they basically say, look, we know that you've got some data that you're trying to compress. So when you get to the decompression stage of things, you've basically got a big buffer where you're going to store the output, right? And this was back in the days when streaming might have been a thing too. So the output buffer itself can actually be a rolling window potentially. But in almost all cases nowadays, it's not. We're literally talking about the whole data that we're about to get. But this works for streaming too. You just have less of a look back. This is where the look back window stuff comes in. But anyway, we have an output buffer that's going to hold the thing. So in our case, right, this is an image. We're trying to like output this image, right? So what's going to happen is the decompressor is going to want information about what it's writing in here for pixels, right? That's what it's trying to do. Or if it was compressing something else, doesn't matter what it is, it's just going to write into this output buffer. What LZ style compressors do is they say, let's have two modes. One is put new data in to the buffer. And another is copy old data into the buffer. Right? So these are the two things we might want to do in an LZ style compressor. And so what they have is they have a stream of data that says which one of these things to do. Am I going to put new data into the buffer, or am I going to copy old data into the buffer? If it's one, then what I'll, imagine a stream that actually had this. If it's one, right, if my mode thing says mode 1, then here is what's called a literal, which just means some new data, right? Literal is just a fancy way of saying put some new data in because, hey, it's literally this data. So the stream, this is the stream this is the input stream to the decompressor, has the mode value followed by the data to put in there, right? So in the case of mode 1, it's just some data. This data just gets copied, right? Bam. Wherever we're writing to, it just gets copied, right? And we advance the pointer, so now we're writing here, right, as we're writing in. If on the other hand, we see a 2, right? So maybe after this, there's a 2. There's a 2 is the next in the stream. Then what we have is two pieces of data that follow the 2, which is the distance. It doesn't have to be in this order. The distance and the size, right? Now in this case, the size may or may not be specified. So if it just is a fixed, like you could have an LZ compressor that says fixed size, it's a byte, let's say, is all we do. So we output 1 byte whenever we're outputting a literal. Sometimes that's true. Or we could have like there could have been a size here that says how big the literal is. That depends on which LZ variant you're using. And it just depends on which gives you better compression, right? But either way, it's a literal. In this case, same thing. We could just say that the size is always the same, but usually the size has to be specified here in order for good compression. So usually when you do copy old data, you specify two things, the distance and the size, right? And the distance says how far from where I'm at, how far back into the buffer should I go to grab the thing that I will then copy and put here, right? And so what this is, the reason this is often called dictionary compression is because it effectively treats the output that you've done so far as a dictionary that you can look up into and grab whole sections to specify new pieces of the stream that are not new at all. They're actually old. So that's why this kind of compressor excels on things like large sections of similar data, because it can just grab old pieces where it was already specified and copy it down. So for example, large runs of the same pattern, very good, right? So checkerboard or anything like that, it can just grab whole sections and move it in. Lots of little gradient modifying, like crazy patterns, tie-dye, really bad because there's nowhere to grab to do it, right? And so that's why PNG is very good at compressing some data and very bad at compressing others, is just because, look, dictionary style compression at the end of the day cannot do any sorts of fanciness to try and compress the data if it's not self-similar, so it had better be somewhat self-similar going into it. And by the way, we can apply some transforms to try and help it be self-similar, but if we can't find a transform that makes it more self-similar that's in the PNG spec, well then we're just dead in the water and the file will be huge. That's just how it goes, right? Now, one thing that's worth mentioning with LZ compressors is there's the hidden ability to do RLE in here. So you know about RLE compressors, right? Run length encoding. Well, run length encoding is basically poor man's LZ, right? Because run length encoding says, look, I'm going to have the same two modes, right? And you've probably seen this before. One is literal, and two is repeat. And repeat will give some fixed length thing like a byte and just say, do this byte 500 times, right? So what you may ask is it possible for the LZ stream to do a repeat? Because otherwise, RLE is actually better for some things, kind of, right? Well, the answer is yes, it is. First of all, there's one way it could do a repeat, which is straightforward. And if you think about it, you can see that it's not as efficient as RLE. That way as well, look, I output one literal, okay? Then I output a second literal of the same kind. Now I've got two. Then I reference the 2 to create 4, right? Then I reference the 4 to create 8, right? And you build it up by powers of 2. So that would give you a log n way of specifying it, but remember, RLE was able to do it in 1. So the question is, can we do better than that? And the answer is, by coding the LZ-style decompressor correctly, yes, you can. What you do is you specify one literal, right? And then the next thing you specify is a distance right to that literal and a size that actually would have right past where the cursor currently is. So here's the output cursor, right? I've read from the input stream, it says go back 1 and get this thing, right? This piece of data. Then I put in a size that's that's my repeat count. So literally the repeat. If the repeat was 60,000, I just put 60,000. And it's like, well, how are you going to copy 60,000? There's only one thing to copy. Well, as long as you copy a byte at a time, it just works. Because I copy this byte into the output position. Now I move my copy pointer forward 1, and what's there? A copy of the byte beforehand. So it copies into the next one, right? And that copies into the next one. And so it cascades forward and effectively does the RLE for you, right? So it turns out in just one mode 2 instruction, I can actually RLE data as well. Because as long as I've outputted anywhere in my back buffer one copy of that thing, well, actually, that's not true. I have to do, it does cost me one literal, right? It has to be outputted, it has to be output right at the cursor, right? It can't be somewhere else. But as long as I put one literal in, then I can specify a whole run that goes as long as I want, right? Okay. So that's just the basics of LZ. It's really just the same as RLE, but instead of always specifying the thing to repeat, like you would in RLE, you specify a pointer into the back data to use. It's literally that simple. There's nothing more to it. So if you've ever done RLE, you've basically done LZ. It's that simple, the decoding anyway. Encoding, as always, is really complicated because you have to start thinking about what the best way to encode something is, and that involves all these trade-offs. Should I put this? Should I do that? Should I repeat here? Should I not repeat here, right? And so that's a whole nother can of worms. But for the time being, we only have to write a decompressor, so we don't have to care about that. We just get the easy part. Anyway, so we're expecting to decode something here with the Huffman table, and then we're expected to look at it and see what it equals. So we're saying basically if it's less than 256, we do one thing. If it's greater, we do another. So if it's less than 256, we're supposed to copy a literal byte to the output stream, right? So what that suggests to me is we'd basically say, okay, our output is 8 bits that we're going to write to our out pointer. And so, you know, we write something there. And then otherwise, we've got this sort of, we've got this loop to do here. And I'm not sure I understand exactly what they're trying to say. If the value equals the end of block, but I don't know what that means, break from loop. Otherwise, do some stuff here. And so I'm guessing... So I'm guessing what it's basically saying is actually this. That this... I'm guessing it's basically saying this. It seems to me like they're basically saying, look, if it's less than 256, you do one thing. If it's greater than 256, you do another thing. Otherwise, that's the end of it. Right? Put that slightly the wrong place there. That's what it looks like to me. So that's what I'm going with. So then what we're going to say here is like, okay, decode the distance value from the input stream. So that's basically saying here, look, we've got the length out of the Huffman decode, but now we need to get the distance, that look back value, right? And then move backwards just a byte in the output and copy length bytes from this position to the output stream. So then we're just going to go like this. Right? The only thing I don't understand here is the length value presumably isn't... Like, you would subtract 256 from it first, wouldn't you? Like, I'm assuming that litlen here... No, okay. So this here is actually that, right? Litlen presumably wants to have 256 subtracted from it here, I would think, right? So I would assume, even though it doesn't look like this from the pseudocode, I would assume that this is actually what you want, right? Because you don't want the minimum copy size to be 256. So in order to get a copy size of 1, 2, 3, 4, 5, which we might want, you're going to have to subtract from it, right? So presumably we do a Huffman decode on the distance, and then we do the copy, right? We do the subtract distance and then the copy. So to do the copy, all we really have to do here, again, is just, well, you know, we'll deal with writing later. And I think that's it. So mostly what I want to know here is that correct? And then how do we do the Huffman decode, right? We also need to know how many bits these are. So let's take a look. So here's a non-compressed block, B type 0. Any bits of input up to the next byte boundary ignored. The rest of the block consists of the following information: len bytes of literal data. Len is the number of data bytes in the block. Len is the ones complement. What? Why? So that's just for safety's sake or something? That I don't understand at all. So it sounds like nlen is literally useless. I mean, we can do this. Because if it's the ones complement, which is, not, at least if I understand correctly what they're trying to say there, I assume that means it's the knotted value. Maybe I don't understand what they're talking about. Anyway, so I think that's what they mean. I really couldn't tell you. So that's looks like what they're doing there. Let's see here for compressed blocks. As noted above, encoded data blocks in the deflate format is a sequence of symbols drawn from 3 conceptually distinct alphabets, either literal bytes from the alphabet of byte values or length backward distance pairs, where the length is drawn from 3 to 258 and the distance is drawn from 1 to 32,768. In fact, the literal and length alphabets are merged into a single alphabet, 0 to 285, where values 0 to 285 represent literal bytes. The value 2d6 indicates end of block, and values 2d7 to 2d8 represent length codes, possibly in conjunction with extra bits following the symbol code as follows. Okay. The extra bit should be interpreted as a machine integer stored with the most significant bit first. Bits 1110 represent the value 14. Okay. So 257 to 285, there's all... So are they saying this is literally just hard-coded? It sure seems that way. It says the extra bit should be interpreted as a machine integer stored with the most recent right. I don't know what that actually has to do with anything, but I guess they're trying to say because you're talking about more bits that are in the stream. But just looking at this, so basically they're just saying, look, we have a number from 0 to 285 that gives you the base value, and then we grab some extra bits depending on what the value is. So it's sort of like we manually made the Huffman table. So this is not an arbitrary Huffman decode. It's like a fixed Huffman table we just say we use always, right? and you're just expected to just decode it exactly this way. What is this table? This is just I don't know what this table is supposed to be. Oh, this is for the distance. So the distance is just 0 to 29, and then you can have more extra bits encoded there. So yeah, it looks like basically the Huffman code is always just for the distance and length, it's always these, no matter what, even if it's dynamic. Okay, that's not, no. So here it says, so I don't really understand why this is written this way. Here's a bunch of stuff that talks about how you would represent the length and distance codes, right? And this is basically a fixed decoding. It's saying here's how to decode it. But then it goes on to say, well, if you're compressing with dynamic Huffman codes, which is B type 10, which I thought is what we were going to be doing, the Huffman codes for the two alphabets appear in the block immediately after the header bits and before the actual compressed data, first the literal length code and then the distance code. So it sounds to me like this is just not relevant. But yet this was defined in a section that made it sound like it would always do it. So I'm not really sure what they mean. Do they mean to say that you will always apply this Huffman, effectively, after applying the dynamic Huffman that you apply first? I really couldn't tell you. That seems a little odd, but that seems sort of like what they're saying. I'm going to go ahead and start investigating that a little bit more. So if I want to consume bits at a time here, I'm going to actually do a thing that lets me do that. So what I want to do is I'm going to go ahead and put a little like side path into my consume thing here that lets me consume bits. And that way I can just see what some of this data is, because that's just weird. I don't really understand why they, if that was, like, that's just a really weird way for them to describe that. So let's take a look at that, and I'm just going to implement these functions here. So we have we have consume bits. Why isn't my B final settable there? What did I do? There we go. All right, so we have two functions we need to do. We need consume bits and flush byte at the moment. And I'm just going to assume that we're not going to do anything bigger than a 32-bit thing here. And that's all I'm going to support. So what I want to do here is just say, all right, my streaming buffer is going to have a little thing in it that's like maybe something like this. Not particularly good. Again, these are not, I would not recommend implementing things the way I'm doing them here. These are just for my convenience for getting the file parsed. If you wanted something fast, you probably would be thinking along very different lines. Anyway, so what I want to be able to do here is I want to be able to implement these two functions. In terms of consuming bits, what I need to do is make sure that I have enough bits in my bit buffer, basically, is what I'm trying to do here. So what I want to do is say, all right, maybe I'll just do this. What I want to do here is say, okay, if the bit count in my bit buffer is greater than or equal to the bit count you want, then I'm going to be okay. I can just subtract the bits away from there and give you back the bits that I've got, right? That's going to be pretty easy. So I'll just have a result here. And I guess what I want to do, so if the buffer's bit count is greater than or equal to the bit count, then I'm going to subtract the bit count away, and I need to copy that amount of bits into what I'm returning as the result. So what I want to do here is I want to give the result, I want it to be whatever the bit buffer is. Obviously, I'm just going to make it give the low bits, right? So I'm going to shift in bits at the top. So I want to give it that many bits back. I assume these, so I guess I don't know what order the bits are going in here is the only thing. Increasing bit number within the byte, i.e. starting with the least significant bit of the byte. So I think we're just fine. So what I want to do is I want to take the bit buffer and I want to mask off any part of it that's not actually requested here. So basically, if you only wanted 4 bits, but there's 8 bits in the bit buffer, I want to just give you back that smaller portion, right? So what I want to do is say, well, you asked for this many bits, right? So let's say you asked for only 1 bit. Then what I want to do is mask off only that section. So what I could do is I can do this, right? I can shift up whatever you ask for the bit count. Let's say you ask for 1 or 2. I can shift a 1 up that many places, which puts the 1 in the next slot, the next bit over from the last highest bit you requested, right? From the highest bit you requested. I can subtract 1 from it, which will make FFFFF be all the way on the bottom. So if I AND with that, I'll get rid of everything on the top that wasn't that you don't want, right? And then I can shift down the bit buffer by that many bits, right? So however many bits you read, I'll get rid of that many, right? So again, this is the same situation as before. If for some reason I can't read that many bits, I'm going to treat that as an underflow. Well, in fact, you know what? I don't really need to do that because I'm going to call that function anyway. And so, yeah, I guess we don't really need to worry about that. So what I want to do now is say, well, all right, what happens if the bit count wouldn't have been sufficient? So the amount of bits I have in the buffer is not going to be enough, right? What I want to do is I want to consume as many bytes as necessary to get me to the right bit number, right? So what I can do here is I could do a while loop, but I don't think I really want to because I know that my bit count doesn't really go above 16 in this case, actually. So I can just use 2 cases probably, or I could just always shift in. I could always just shift 16 in, because if you're less than 16, I know I can shift in 16. So I'm not sure, yeah. Maybe I'll do this, and I'll just say, well, let's just assert that the bit count is less than 16, right? Something like that. So assuming that the bit count is less than or equal to 16, then what I want to do is I want to shift in I want to grab from the data stream the new bits that I'm going to actually process as we go forward, right? And so what I want to do is I want to grab those bits, and like I said, I don't really know about the least significant, most significant part of this, so we're going to have to see if I'm getting the data correctly here. We'll find out as we go. But what I want to do is I want to grab the values from the buffer that I'm trying to consume here. I want to kind of go, and I think I want to go byte at a time. So actually, you know what I'm going to do? I'm going to do this the piggiest way possible. So I'm just going to keep going here, and I'm going to say, well, I can't do it. I'm going to start shifting stuff in. So I'm just going to say that, you know, I've got a U8 here that's my byte. I'm going to consume 1 U8 worth of data from the buffer, and I'm going to go ahead and pack that byte into the correct location in the stream. So I'm going to say I've got 8 more bytes, right? And I guess before I do that, I want to OR in this piece of information. So that byte, I'm going to, well, you know what, I can do this. So that byte, I can shift up by the current bit counts and OR it in. So that should allow me to read from the stream and pack in exactly as many as was requested. When I go to flush the byte, that's really simple. If flushing a byte is just saying, look, the bit count is now 0, and the bit buff has nothing in it, right? So that's really pretty trivial. And I think that's mostly all I need. Now there's probably bugs in there because, like I said, and I don't really know if we're interpreting the spec correctly there. So we'll see what happens, but that's mostly what we want. So let's just take a look at what's going on here. So if I want to consume 1 bit from the data stream, oops, I accidentally deleted the B final there when I was copying it. I still do want to set B final. There we go. So when I want to consume 1 bit, let's go in here. The buffer bit count should be 0 and the bit count is 1. So what I want to do is read 1 byte. And then what I want to do is OR that in. So it should just be equal to the byte now. It should just be 236, and it is. And our bit count should now be 8. So now I should be able to read it. The bit count should go down by 1 to 7. The result should just be whatever the bottom bit is. And I think this was an even value, so the bottom bit must be 0, right? Yeah. I think that's right. And so then we just say, okay, and now we're going to shift it down and process the new value, right? So I think we're good. So that just grabs a bit. There's my bit. It's 0, which is what we would expect because this is probably not the last block. Then we need to consume 2 bits. So let's take a look at what happens there. In here, we should be fine because we consumed a whole byte last time. So here we say, all right, as if we're okay, let's see what the bit count is now. Well, the bit count is going to go down again. It's going to go down to 5. Yep. So now let's see what our result is. Our result is 2. Hey, look, that's exactly what we thought it should be. So we need to read the Huffman codes, which we're not currently doing. And then we would keep going, right? So I think we're sort of starting to get the hang of it here. We're just getting to get our minds in the space of the ping spec. Now, you know, like I said, there's a long way to go, so maybe not, but we haven't completely been sort of confused yet. We'll get there. So when we do need to read the Huffman stuff, I correctly guessed that it would be that type, so I think we're reading the spec right there. So we want to look and see what it says about reading that data in. It was really obtuse, if I remember correctly, the way it said it, but let's see. Here we go. The Huffman codes for the 2 alphabets appear in the block immediately after the header bits and before the actual compressed data. First the literal length code, and then the distance code. Each code is defined by a sequence of code lengths as discussed in paragraph 322 above. For even greater compactness, the code length sequences themselves are compressed using a Huffman code. So it looks like it's just saying use this ridiculous nonsense to decrypt what we're telling you. A code length of 0 indicates that the corresponding symbol in the literal length or distance alphabet will not occur in the block and should not participate in the Huffman code construction algorithm given earlier. If only one distance code is used, it is encoded using 1 bit, not 0 bits. In this case, where it is a single code length of 1 with 1 unused code. The distance code of 0 bits means that there are no distance codes used at all. We can now define the format of the block. So there's 5 bits of HLIT, 5 bits of HDist, 4 bits of HCLEN, This is nuts. This is one of the things where I guess they kept tweaking it to they were getting better compression or something from it. So you see a lot of this weirdness here. All right, well, let's start reading it. So let's read HLIT first. HDist. And HCLEN. So these say the number of literal codes minus 257, the number of distance codes minus 1, and the number of code lengths minus 4. So what we want to do to get those to their actual values is we want to basically say add in the 257, add in the 1, and add in the 4. We then say HCLEN plus 4 times 3 bits worth of data for the code lengths. So I think that's just saying we're going to do a loop of hclen plus 4, which I'm assuming they actually don't mean hclen plus 4 after adjusted. That's the plus 4 that we already did. So we're going to read 3 bits that many times. Right? Then we're going to read hlit plus 257, which we already did. That many, read that many, read that many. Right? All right. So that means we start here and we read to hlit like so. And what I want to do here is I want to consume 3 bits for each of these. And what that is the code lengths for the code length alphabet, which is this thing up here, I guess. So code length alphabet given just above in the order 16, 17, 18, 08, 7, 9, 6, 10, 5, 11, 4, 12, 3, 13, 2, 14, 1, 15. Why would it be in that order if this data isn't itself compressed? Why would they give it in an arbitrary order, though? That's a doozy. I'm not sure I understand why you would like arbitrarily muck with the order. If I'm reading that right? I mean, that's what we're saying. Are we? I mean, is that really what we're saying? Maybe they mean something else with that. The code lengths are interpreted as 3-bit integers. A code length of 0 means the corresponding symbol is not used. I feel like there's no reason for these specs to be this obtuse. It should just be straightforward to explain. I don't understand this, but I guess people don't know how to explain things usually. The Huffman codes for the 2 alphas appear in the block immediately after the header. First, the literal length code, and then the distance code. Each code is defined by a sequence of code lengths as discussed in paragraph 322, which is this nonsense. So all we need is the bit lengths, which is what we're saying here, right? We're just providing how many bits per thing there are, right? And then we're going to run this constructor on it, which seems fine, right? That all makes reasonable sense. For even greater compactness, the code lengths themselves are compressed using Huffman code. The alphabet for code lengths is as follows. 0 to 15 represent code length 0 to 15. 16 is copy the previous code length some number of times, right? 17 is this, 18 is that. So that's fine. Yeah, I just can't quite figure that out. The swizzle thing I just don't get. 16, 17, 18, 0, 8, 7, 9, 6, 10, 5, 11, 4, 12, 3, 13, 2, 14, 1, 15. So if those... Okay, all right. You know what? I do think I know why they're doing that. So hclen probably tries to compress how many of the litter of these it actually stores by packing in this order, because they think that if they pack them in that order, oftentimes this is the order that makes it so that you can use the repeat codes maximally. Like 16, 17, and 18 tend to be specified the same way. So we put them, and they're usually yeah, okay. Man, oh man. All right. If that's what you want, man. So all right, let's see how this needs to be specified then, because the hclen is actually telling me how many of the things I use like when I'm reading. All right, so when I read one of these things, I know that so the thing that I didn't understand was that I was assuming like, okay, you probably just specify all of them. They don't want to actually even specify all of these. They're trying to compress it below that amount. So I guess what they're saying is like, okay, the hclen will probably, hopefully, most of the time be less than that. So I mean, I can also do this. I don't know why I said hlit there. It's supposed to be hclen. So anyway, now I say read the 3-bit integer, right? And the 3-bit integer is this thing. So this is like an encoded length. And then I want to say like, okay, if the encoded length is greater than or equal to 0, well, I don't really do that. If it's just less than or equal to 15. Else, if it's 16, 17, or 18, I'm just going to print that out and say we're in a bad state, right? So if it's 0 to 15, we just use it, right? If it's 16, we copy whatever the code length is we used last time between 3 and 6 times, and the next 2 bits indicate repeat length. Now, what I don't understand is, are you saying to actually use that now, or are you saying that will come later, right? Because if that's the case, then that means that this actually gets read in between the reads for these, which it doesn't specify here. And I'm not sure if that's what they mean. The next 2 bits indicate the repeat length, right? There it is. Yeah, so I'm obviously not understanding this correctly. Because let's say you were going to actually implement this right off the bat. So they must mean after this. I don't know about the so I still don't know why this order would make any sense. Because if you're going to read all of these in, why would you care what order they were in? Right? Why would you care to swizzle them like that? I just can't get past that. It's throwing me for a loop. Because I don't understand why we need to swizzle it. HLIB assumes code links to literal length alphabet and code use. Those both make sense to me. So I feel like there's just one thing I'm missing in this steps that I don't understand. I don't understand this swizzle table. I just don't understand where it goes. What it's swizzling. But it seems to me like I would want to do, when we encode this stuff here, you know, I've read HCLan. It can only be 16 plus 4, so it can only be like 20 or whatever, right? I mean, it can't be, it can't exceed 20. So, you know, we know that effectively it just, I don't know, seems like they're telling me to do this. And that those are going to go directly in there. And then after that will be the decryptor for, decryptor is probably not the wrong word, decompressor, quote unquote. These guys will definitely go through the other code. The code link fields can cross from HLIB to the HDIS plus 1 code links. In other words, all code links from a single sequence of HLIT plus HDIT plus, okay. So the other thing it's telling me here is that we just have one Huffman table, well, not one Huffman table. We just have one decompression block that we're basically doing here, which is whatever this thing is. So I also know that I've got like my, I don't know what you want to call this, my len table or whatever. And that thing is going to be at a maximum, it's like, so 64, you know, that thing can't be bigger than like 512 or whatever, right? So when I come in here, I know that I can use, like when I start decompressing these, I don't actually have to treat these two things separately. I can just say, look, the total number of things in the length table is just going to be equal to the HLIT plus the HDIST, and I can do them the whole, I can do the whole thing. So that's nice. There's just one decompressor that just does the decompression directly. And that's, you know, way better, right? So since these are all done with the Huffman code, and again, I'm just not sure how this part boils down here. The alphabet for code lengths is this. But then I don't really know what this tells me. Yes, I do. Okay. So what this tells me, well, you know what? No, I still don't. Because I still don't know why you need to swizzle it. Why can't you just put them in the order 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So even the thing that I just thought, I was like, okay, no, I see why this, I still don't. I still just can't see it. Because it looks like they're always storing 3 bits for each one of them. So if you're always going to store 3 bits for each one of them, then why would you ever need to do anything different? I just can't get past it. I got nothing. Everything else in here seems to make sense to me, but that one I just can't figure out. Why would you specify a swizzle table for data that you weren't compressing? Why would you ever care what order it was in? I've got to be missing something. They must be compressing it or something. Because if you're not compressing it, why would you swizzle it? What am I not thinking of? I mean, I can stare at this 1,500 times, but I'm just not seeing anything different. It says right here, it reads 3 bits for each of these. But if it's reading 3 bits for each of them, why would it... Maybe it's talking about this order as being applied somewhere else, actually. Or maybe they just swizzled it just 'cause? Why would you do that? I don't know. I have no idea. I mean, it looks to me like this is what's going on, right? That's what it looks like the spec says. What is this doing here? It doesn't do anything, right? I mean, there's no point to that. Like, I just don't see... I don't see how that gets me anything. So, you know, we get in here, and, you know, assuming that we interpret the rest of this correctly, here's what we ended up with. H-cleanse specified... I got it. I finally got it. It's because if you weren't going to specify all of them, these are the ones they think you're least likely to specify. Okay, so you are compressing the lengths sometimes, which is to say you're going to truncate them, right? So maybe I only specify up to there. Well, if I only specify up to there, they're pre-saying the most likely things I need to specify are like 16, 17, and 18. Okay. So that's why they... Okay, so that's what it's there for. I should have thought of that before. Makes perfect sense. It's just saying, look, we're going to truncate these sometimes. Here's what happens when we truncate. Did I do something wrong here? No, I didn't. Okay, there we go. So this fills in all the lengths. And that's fine. So we get to here, and here are our code lengths, right? For the length compression. And that's all good. And hey, 18 is all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, wait. No, it's not. But 15 did get filled in. What just happened? So when did 15 get filled in? Oh, that's the swizzle. There we go. So 18 is missing 1, so 15 just doesn't get specified. Can I see this table, please? Oh, of course, it won't show me the table anymore because it has exited the scope. Thank you, Visual Studio. Worst feature ever. All right, well, anyway, I'm satisfied now that, that was weird, that helps me not freak out about that. I'm okay with that. So all right, so that's all fine. So that's just telling us what the truncated, that some of the values might be truncated. So I'm cool with that now. Code lengths to the above, code length given in this order, fine. The code lengths are interpreted as 3-bit integers 0 to 7. As above, a code length of 0 means a corresponding symbol, literal length, or distance code is not used. So basically, if you read a 0, it's not. If we don't have all of them, I'm not sure what that would mean. I assume it's just a 0, so it just means like we never used one of those lengths or something like that, right? Okay. So what we need to do now is we need to write the thing that builds a Huffman table out of one of those, because all the rest of these are going to come from that Huffman table, right? So what we need to do here is we need to have something that can take the hclen table that we read and turn it into a Huffman decoder in some way, right? This could really be phrased like this. Because we know that's how many we're going to have, right? So then what I want to do is say, all right, let's produce or I don't know. We want to create the Huffman table here. So we need some way of making one of these. So we need like a PNG Huffman. And this is our length Huffman. Or this is, sorry, this is our dictionary Huffman. So we need some way of creating one of these Huffman tables from one of these length codes, right? And so we know that this is the length codes that we have. We know that, well, I guess I don't know exactly what they want. They may want this, or they may want hclen. I'm not sure. I'm not 100% clear on that aspect of it, actually, so we'll talk about that in a second. But then, once we're done with that, then we know that we're going to make another Huffman table, and we're going to make another Huffman table out of the remaining stuff that we get here for literals and distances, right? So once we compute this Huffman, then what we want to do is we want to do a Huffman read from our stream. And we need to give it this Huffman dictionary to operate on. So basically what we say is, look, decode the next thing here, and that's going to be decoded as a length that gets put into this table. And what it suggests here is that, well, actually, I guess this is still encoded length. So the encoded length itself is then interpreted this way. and we write that into another table that then does the exact same thing. So we have like a PNG Huffman that's going to be for the actual data, right? And we've got one for the literal Huffman and one for the length. Those are going to get generated out here somewhere. And used. Yeah. So basically this should be looking like that, more or less. And I think, yeah, that's it. The distance... Sorry, it's lit len and distance. Am I right? Yeah. So we've got a lit len Huffman and a distance Huffman. So what we want to do here is when we decode, the lit len Huffman is used for the lit len, exactly as you would expect. And the distance Huffman is used for the distance. So this actually looks like that, right? And this is the thing that produces the tables which then are used to do the Huffman computation here. So now, I'm just not sure about this part. I don't know whether this should really be hclen here. I don't know how we want to do the Huffman in terms of the codes because it'll just be zeros after. I don't know if it's important for it to see those zeros after or not. That's kind of... I'm going to go ahead and say not for now. So what I'm going to do is I'm just going to say that hclen comes in here. So what I'm going to do is I'm going to say for these, the same thing is true. I'm going to pass the actual ones here. So we know an hlit and an hdist for the two of these. Oops. So getting those two Huffman tables will be done by taking the sort of raw table here. So there's the length table, and here's the like lit len dist table for whatever. I don't know how we want to specify that. I don't need to clear that one. I guess technically I do need to clear this one. I don't need to clear this one, I guess, because these go in order. So this one is just however many the maximum would it be of these. So we know that that's not, oh, already had that right here. So I know I've got this and I can just write into it as we go. So what I need to do is do the Huffman decode and then I need to like write into the table this way, right? So yeah, this index is not particularly useful. So really I want lit len count here to be sort of something that I write to. And what I need to do is I need to do this decoding before I can do the rest of this, right? Now in theory, if I know how many hlit there are, that doesn't necessarily help me, because I guess, is this always a fixed length? Yeah, so I'm not sure exactly how that table gets interpreted necessarily. I think it's just hlit and hdist is the count on each of those. So I think but since those encoded lengths involve repeats, yeah, I'm just not sure about that. So I'm not sure exactly how they expect the table to then be used. I don't know if what they're saying is that they... Because the HLIT here, yeah, this just really doesn't give you the information you need. I feel like there's a little bit of a subtlety there I'm not understanding as well. So here's what I think it's saying. I think what it's actually saying is that HLIT plus HDist is actually the output size, not the input size. So I think you don't do this. What you actually do is this. Right? I think that's what it's actually saying. And then you do this. Does that make sense? So we're basically saying, look, here's how many you're going to get. But we're not going to tell you how many actual pieces of information we're going to use to encode that, because sometimes we're going to encode repeats in here, right? So what we want you to do is just keep reading from your Huffman, from the table we gave you before. Keep reading from that till you've filled up that table, right? And we should be able to assert here also that it's exact, because if we mess up the stream read, then it won't be exact, so that should tell us as well. And then what I want you to do is produce the Huffman from those input values that I've given you, right, encoded in this way. And these are encoded based on this. So again, if the encoded len is less than or equal to 15, that's actually the code, right? So the lit len dist table is actually going to just encode exactly that length. If it's a 16, these are zeros. Both of these are zeros. So if it's a 16, we read 2 bits. And we can also do well, I guess we don't really have to do that. So we consume 2 bits from the input stream here, and we just rep that many times. So this is like an RLE. So our rep val is just whatever the distance table's previous value was, right? Now we can assert here that the len count is greater than 0, because if it tells us to repeat something and we haven't gotten anything, that sounds like a bug. So I'm just going to go ahead and say that that has to happen. Then what we can do is do the zeros really easily. That's just this. Right. Another way to do this that's super fancy, if you wanted to, is you could do this. Right. So this way it's always phrased as a rep, and we just set the rep count and the rep value correctly in each of these cases. In this case, we set it to a rep count of 1 and encoded length, and use the encoded length as the value. In this case, you know, well, you see what I'm doing, right? It's pretty basic. Let me just read these here, how this is next to length. 0 equals 3, 3 equals 6. So I think this is here, the rep count is supposed to be 3 plus the value that we grab, right? I think. So code's 816 plus 2 bits. 1116 plus 2 bits will expand to 12 codes. I don't quite get that part. 16 plus 2 bits 10 will expand to what? I'm going to ignore that for now. Repeated code is for 3 to 10 times 3 bits of length. Okay, so that's just, again, this is the same thing. And then for 11 through 7 bits of length. So this is just that. Right? So that, I guess, is what they want from us there. And so then we can make our next weekend's job to do the Huffman table construction. And that'll probably be nasty, but that's like the last thing then, because it looks like we've got everything else. So then we're just on to debugging, which of course is going to be an unenvious situation, but you know, what are you going to do? I should say input count, input PNG Huffman results. So, and then decode Huffman. Yeah. And I think that's what we're talking about. If I'm not very much in error. So there we have it. Yeah, I guess I'll go to brief Q&A, but I think that's pretty much it. I'm sure we'll end up in a debugging nightmare with it as we try to figure out how, you know, how all these things are coming together. But I think that's everything. I think that's a complete sketch of the algorithm, unless I missed something in there. So we just need to go back and implement now that that Huffman code decompression step, like calculation step, and then we have to put it in some format that we can easily actually use to implement the Huffman tree. I'm happy you're doing this. I've had problems making my inflate decoder for fun work, and you being a spec decoder works out perfectly. Okay, cool. Ratchet Freak says, I believe the length for the LZ should be interpreted like U32 copy length equals length table base litlen minus 257 plus consume bits. Do you mean this length? Yeah, okay, but you're talking about down in here, right? Which we haven't really quite gotten to yet. How have you found the PNG and ZLIB specification compared to other specifications you have read and implemented? Um, I guess what I would say is there's two ways that specs can be bad. One is the spec can be incomplete, and one is the spec can be obtuse. I would say these seem to be relatively complete, but quite obtuse for no reason. Um, you could compare that to, for example, the PSD specification, which is the opposite. It is very easy to understand the specification, but it is very incomplete. Um, and so ideally a spec should be both. It should specify everything, and it should specify it in a clean and concise way that's easy to understand, right? Um, so any way to fix the pink flashing? It was fairly persistent to say, you'd have to ask Alan. That's as far as I know, that's in 4Coder. I can't fix it. So, no, the art will probably not be iterated live. It's more just for them to be able to work on it. What do you do when you have an incomplete specification? Is it then more just trial and error, or are there techs how to continue? Well, there's a couple things you can do. So for this particular stream, I'm just going with the spec for a while. And when I hit we haven't yet, but if I hit some part where I cannot figure out from the spec what they meant, I can go look at reference implementations, which is a good place to go, right? So I'm just showing some different steps here, and we'll go to that if we have to. But for the moment, I'm just coming from the spec because so far we've been able to do so. And so far we've gotten far enough with that it's fine, right? But eventually we may have to go to reference implementation. That's the first thing to try to do. If you don't have a reference implementation and you're kind of the first person in there trying to like hack around, then yeah, what you have to do is trial and error, but you can give yourself a little bit of a leg up on the trial and error front by trying to feed structured art into the thing at the head end so that you can, it's basically like differential cryptanalysis, if you've ever looked at that. Differential cryptanalysis is a way of fussing with the input stream to an encryptor and looking how the decrypt, what the data comes out of the other end after encryption. That same technique can be used to much greater effect on reverse engineering, right? When you're trying to figure out how a file spec works and you have an encoder, and you're trying to write a decoder, what you can do is just like feed different art into it, like a block of all red, and then a block of all blue and whatever, and then a block of alternating red and blue, right? And then you can hope to try and get different things to happen in the stream that will be clear to you, because like, oh, okay, the dictionaries only should have like one thing in it or whatever, so I can help, right? You can construct cases that you think will create encodings of a certain nature and work backwards from that, right? The other thing you can do is, if you're a reverse engineering kind of person, is you can reverse engineer a decoder. So if you don't have source to a decoder, but you do have a program that does it, crack on in there, right? That's a nasty business, but there's people who do that a lot and get good at it, so you can do that. What 4Coder version are you on stream? I don't know. Is there any way to tell? I don't know how to tell. Branch decoder just caught up with the stream, but I have had a question for a while. When you come up with a reusable data structure and want to share it between projects and other people, how do you deal with custom allocation? I have been writing some hybrid data structures and I want to add custom allocation, but adding a template parameter seems like a bad solution to the problem. Well, oh, sorry, just to finish the last question. You said there's a messages window which has it. There you go, 4025. So yeah, I guess what I would say is the first question is, are you sure that you need to do allocation? And I know that sounds like an odd question, but I really mean it. Are you sure that you need to? A lot of times you don't actually need to. This is a little off topic, but for example, the way I did it in Granny is there's 3 calls basically for everything that allocates data, and they look like this. So this is the way everything worked in Granny. So anyone who just didn't care where the memory went, it would just go create thingy and Granny would allocate the memory, right? And if you did care where it went, you would just call get size of thingy and you'd pass the same parameters you're going to pass to create, and then you'd call put thingy in place, and you'd pass the memory that you allocated that was, you were basically warranting that it would be whatever size came back from this, right? And that's just how it worked. So what would happen is when you do construction of something, you would just say, okay, I know I need this much space to store all the parts of it or whatever, so I just did that. And this actually worked for 99% of all the things that the library needed to do. There's once in a while where you actually had allocation that wanted to happen behind the scenes at arbitrary times, but a lot of times that's just not necessary. So the first thing I would say is don't actually do custom allocation anywhere you don't absolutely have to. And by absolutely have to, what I mean is don't do custom allocation anywhere where you could have allowed the user to pass in the memory that you should use. Almost all things can be done that way. There are very, very, very few that actually need to have that happen. And so I would just really encourage you to look at that first. And then move on only after you've completely assured yourself that there's no way to implement it in that format. Why does no one spec the simplest solution possible so people can easily implement the parsers and exporters they need in cases where space speed does not matter? Well, I think the problem is that people drastically overestimate the cost of being under flexible. So here's what generally happens. Somebody specifies a good file format. And the file format's like, hey, we want to store pixel data, So we said the width and the height and like one compression format, and then that was the data, right? And that's super great and it works and everyone's happy, except now someone's like, oh, but I really wanted to store like some copyright information in the file, or I wanted to store some information about my like layer data or whatever, right? And so when that person goes to make a new file format because they need these things, in their head what they're thinking is, I don't want to get in another situation like we got into last time where we had to make a whole new file format because I wanted to add some things. So what I'm going to do is I'm going to make a file format that's super flexible and has all these different pieces that can be added to it so that we never have to have another file format again. And everything is going to be here in the TIFF file format, right? That's like the MPEG-4 spec. It's like the TIFF spec. It's like, you know, Og Vorbis or something, right? And these are all about packing 8 billion things into the file format. That helps nobody. These are just not good specifications because nobody implements complete writers, nobody implements complete readers because doing so would take years, right? And it's just not useful. Specify something simple that gets a job done well and use it. And when you have something else that needs to happen, do something else, right? That is way better than this whole nonsense, right? I don't even think you should do stuff like put indexed and true color things in the same file format. Why? They're totally different, right? They're really very, very different. We don't need that stuff. I mean, maybe that's a bad example because it's not that big of a change, right? But it's just like, pick a narrow set of things that you're trying to solve and just do it, right? And be done with it. And then everyone can use that. And if we need something else, we'll use something else. But that way we're clear on what this thing does and everyone can support it easily, you know? Are you going to do audio formats next? No, I'm happy with the WAV reader that we've got in there now. That's totally fine. All right, looks like we're all done. All right, thank you everyone for joining me for this episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along the stream at home, you always can pre-order the game on handmadehero.org. It comes with a source code so you can play around with it. I will be back next week when we will take a look at constructing those Huffman tables, which is the primary thing that we're going to have to do in order to decode the rest of the data. I think we're in pretty good shape. I'm sure we'll have a lot of debugging to do, but basically that is the last step in the process in order to get a decoder functioning, although perhaps not functioning correctly. And then we can go through and figure out what stuff we missed. But that's really where we're at. So this hasn't taken too long. I'm pretty pleased with that. But we'll see how it goes next weekend. Maybe creating and using the Huffman tables will be a giant disaster. Who knows? We'll find out. All right. Hope to see everyone back here for that next week. Until then, have fun programming, and I'll see everyone on the internet